For reverse engineering, you should have a good understanding of assembly and C language. Or if your goal is emulator development or get a better understanding in C, the best place to start is with a CHIP-8 program. We are going to make CHIP-8 emulator. We can't call it an emulator actually, it's more like an interpreter. CHIP-8 was primarily used for creating simple retro style video games, but it doesn't have any physical components. It's more like a set of instructions and a virtual memory. So we can't call it an old computer that was used to play games. It's more like an interpreter, like a computer inside a computer. So let's make it. Let's start by creating a makefile. So we don't need to type in the code again and again to compile. We just need to type make. Before coding it out, we need to know what components does CHIP-8 have. So let's go to my blog. I will link this in the description. CHIP-8 have a 64 pixel wide and 32 pixel tall screen. We will be using SDL for the display. We will talk about SDL more in the code part. So all the links and commands for how to use SDL in this project will be in the resource section of the blog. The next component is memory. All the memory in CHIP-8 is RAM. The memory should be 4 KB or 4096 bytes from location 0x000 to 0xFFF. The first 512 bytes is where the original interpreter is located. The point to note here is 0x200 is where the instruction starts, so our program counter should be pointed at that address. I will show you the memory mapping for a better understanding. This is how the memory of CHIP-8 looks like. The bottom section from 000 to 1FF is where the interpreter. Then our instruction will start from 0x200. You will understand it more when we explain the code. So let's move to the next component. Registers and stack. CHIP-8 has 16 8-bit data registers named V0 to VF. In this, the VF register is used as a flag for some instructions. The stack is 16 bits and it's used to remember the current location before a jump is performed. So the program counter should be stored in the stack before you perform a jump. We also need to implement a stack pointer to remember which level of stack is used. Now the keypad of CHIP-8. It looks almost like this. CHIP-8 has a hex based keyboard. So we should map our keyboard to CHIP-8's keyboard in this manner. This is our normal QWERTY keyboard and this is the CHIP-8 keypad. I will explain more about the other components in the code part for better understanding. Let's move on to the code section. In the coding phase, our first goal is to show an IBM logo on screen. You must do the coding phase step by step to avoid errors. So first, use struct to declare everything we said in the component section. The memory, register, display, program counter, index register, stack and stack register. Then we should declare it globally. We are gonna use the pointer in all the sections. Now add the font. Font is required because CHIP-8 programs often display hexadecimal digits from 0 to F. The font set is a predefined set of pixel patterns. You don't need to worry about typing that, just copy paste that section. While you are watching this video, git clone my repository. I will link it down in the description. I have commented on each line of the code for better understanding. Now call the pointer and use memcopy to copy the font to the memory. Now clear the memory, register and screen. For that, write an initialization function and use memset to clear the memory and set all the bytes in the memory block to 0. Clear the program counter and the index register. Then write a function to open the program file and check if the file is opened. Here our program file is the IBM logo file. Download it from my Git and add it to the same folder where you are writing the code. Use fopen to open the file in read binary mode. After the file is copied, read the instructions using fread. Then point program counter to the address 200. This for loop is for printing the memory contents onto the terminal. I wrote it for debugging purpose. I will run the program and show you the memory contents. This is what I was talking about. After pointing the program counter to the starting address, let's write a loop for fetching, decoding, and executing the opcodes. Opcodes means instructions. This is the most important part. So I will provide a link to the opcode table. First, let's fetch the opcode. So let's call the memory inside the C8 pointer. Each element in memory is 1 byte or 8-bit long. So to fetch one 2-byte opcode, you need to read two consecutive bytes from the memory. Now the decode and executive phase of the opcode. So for that you need to know how to handle the opcodes. To handle the opcode, we are going to divide and conquer it. So an opcode or an instruction is 2 bytes long. We are going to divide it into type, nibble 1, nibble 2, and nibble 3. So each opcode is 2 bytes long, which means 16 bits. So we are going to divide it into 4 bits, each given their perspective names. So it will be easier for us to separate the instructions, and we are going to use switch case to separate each instructions. If an instruction starts with a 0x0, then it goes to this case, or if it starts with 0x6, it will go to another case. Let's start by extracting the first 4 bit, which is the type. For that, we need to right shift 12 bits so that the 4 bits in the front section goes to the last section. We need to assign all the bits in this manner. So now the question is how we can decode. For that, we will take this instruction 00E0 and see how we can decode it. From this instruction, we need to take the first 4 bits as type. So in this case, type will be 0x0 and NNN will be 0x0E0. I think now it's clear to you. 0x as prefix to indicate it as hexadecimal. So now in our switch case, we call the type and matches it with our cases. As our 0x0 matches with our first case, we go inside that case. What if our opcode starts with a 1? So let's check an opcode like that. 1 NNN. Jump to location NNN. So in that case, we will go to the next case where 0x1 is used and go inside that case. Okay, so inside our case 0x0, we again start a switch case because starting with 0x0, we have two instructions. So we again divide it using NNN, which is the last 12 bits. As we only have two instructions, in this case, we do not need to divide anymore. So inside our 0x0E0, our instruction says to clear the display. So we use memset to clear the display. Like that, write all the opcodes. Use this documentation and the Wikipedia page to complete rest of the opcodes. So complete it till CXKK. Do not copy paste the opcode. Do it in your own way, or else you won't learn anything. I have purposefully made some bugs in the code so that you can't do that. So if you are using my code, then you can try to debug it. I have a video in my channel on how to debug using code LLDB in VS Code. That will be a great help while you run into errors. I will add links to the video and all the sites I have shown in the description. Now let's set up the display for IBM logo. Before doing that, we need to set up a case where if the program counter goes beyond our chip-8 memory, then the while loop should stop. For that, at the end of our while loop, we will increment the program counter to go to the next address, and also if our program counter goes beyond our chip-8 memory, then the running will be set to 0 and it will stop the while loop. And we should also close the file we opened in read binary. Inside the main function, give argument count and argument vector as parameters so that we can give the file name dynamically. Now we need to allocate the memory for our chip-8. For that, we are going to use malloc. Malloc is a runtime function, so we are going to use malloc to allocate memory on the heap at runtime. We will clear the memory at the end. Now create a pointer file name to store the address of argument vector and pass it to CHIP-8 function, which is the function we use it to open the file, read the file, and fetch, decode, and execute the opcodes. If you don't know how reference and dereference of pointers work, I have a video on that. I will link it down in the description. Now pass in our C8 pointer to our initialize function. That is the pointer we use to access all the CHIP-8 components. Now let's get started with the display part. For setting up the display, you first need to install SDL2. So all the links will be in my description. And after installing SDL2, include it in our code. Now come down to the main function, then initialize SDL, then initialize display, add an if to check if the display is initialized, then create render and create texture. All this code is available online. You just need to change the parameters in the way you want. So I will link all of this in the description, or else you can check out my blog where I have written it in detailed manner. See, you just need to change the parameters. You can check my GitHub code for reference. After all the initialization, creation, and error handling is done, now at last we need to clean up. For that, we use SDL destroy texture rendering windows and SDL quit, and also free C8 pointer to free the allocated heap memory for our CHIP-8 program. If there is no error, then open the terminal, type make, and run the program with our CHIP-8 program IBM logo. It will work fine. We have reached the first goal. Now the next part is we must map the keys. It is needed for many other opcodes. Use code LLDB in VS Code for debugging if you run into errors. Now let's see how to map the keys of CHIP-8. Carefully look at my terminal. I have written a program to show you that when you press a key, a scan code, often represented in hexadecimal, is sent. That's how the computer knows which key is pressed. So I have pressed here QWERTY and these are the codes. Now use the SDLK to map the QWERTY keyboard to the CHIP-8 keyboard. After that, start the event loop for capturing events like the key press. In the event loop, use SDL key down to check if any key is pressed. If true, then write a loop to check which key is pressed using key code. Check if the key code generated by key press matches SDL defined constant like our SDLKA, SDLK1, etc. If true, then change the state of the key to pressed. Now write the rest of the opcodes. I have written comments in each line of the code, so if you have any doubts, go through the code and read the comments. After completing the opcodes, there is a program to check if your opcodes are working and which is not working. I will also add this in the GitHub. In the repository, there is a section called ROMs. In that, there is a program called test opcodes. I'll show you in a moment. Inside the ROM, see the test opcodes.ch8. Run that. If your opcode is running fine, it will give an OK. If it's not, it will be like the bottom two codes. So go check what's wrong with that. This is a good way to debug. So I'm ending my video at this point. I will do the rest in another video. This video is getting a little longer. So hope you enjoyed and also follow for more. If you want to go a step further in emulator development, your next goal should be making a RISC-V emulator. Then write a Game Boy, then Game Boy Advance, which involves some graphics. So as you challenge yourself, you will learn more. Also check out my Git repository. All the CTFs, bug bounty blogs and videos will be, and also reverse engineering challenges will be in that repository. So that's it. This is my channel. I make videos on bug bounty, reverse engineering and APK. I also have another channel for creating bug bounty contents in Malayalam. I will be uploading soon in that channel.